Hi everyone, we are Group G. We are here to present perceiver, general perception with the iterative attentions. So this is our outline for presentations. We will start with the introduction and motivation, then go through architecture, experiment, operations, and finally our conclusions. As a motivation for developing perceivers, author mentioned that as a human, we can processing all high dimension inputs from multimodalities such as vision and auditions. The modern models using a deep learning, on the other hand, are more designed for individual modality. Those models introduce a helpful inductive biases, but not flexible multimodalities input. And most of the attention based architecture are quadratic time runtime, as the author want to implement a models that are capable of do a close job or even job better than humans performance, which are able to accept different modalities of inputs and can execute in a lower runtimes. That's the main motivation for the author. So going to the perceiver will accept images, videos, audios, point cloud, and something need to mention that is that author didn't using textual modalities in his paper. Using a image as an example, different from other transformer, it take a byte arrays instead of image patches from raw image. And here is some key aspect, including byte arrays, which is input, and the latent array, that's the learn query, the cross attention module, the latent transformer, and also other different from transformers is that transformer output sequence is that first self-attention, then cross-attention. Perceiver is offset, is perform cross-attention first, then perform a few time of self-attention. And as I mentioned in last slides, the transformer has a quadratic time complexity, while perceiver reduce complexity near to linear with respect to image size and the latent vector. So to put everything together, the basic architecture for it is that the perceiver take a high dimension input by array and using the cross attention module to project to a fixed dimension latent bottleneck before processing it using a self-attention block in the latent space. The perceiver attend to the input data by array multiple times by alternating cross attention and the latent self-attention block. Through this build, we were able to achieve a reduce of complexity and a set of multiple modality data. Next, I will give it to the Brandon to explain more on the architecture.
Can everyone see my screen?
Yes, we can see.
Okay. Okay, so as Dunquan mentioned, this is the basic architecture. And we see it uses a byte array as the input. This will be our images, video, audio, and point cloud. And then this latent array, which is a learnable array.
Can you talk a little louder, Brendan? Can you talk a little louder? Yeah, come closer.
Yeah. So I'm going to go into the cross attention first, because this is the key to reducing the runtime. And then we'll get more into the latent transformer and whatnot later. So for the cross attention, it uses the latent array of size n cross d, which is a learned array. This latent array is used to get the queries. And then our byte array, which is size m cross c, is taken directly from the input. So our images, video, audio, and point cloud. This is used to create the keys and values. Now, n and m are going to be our number of tokens. So there's n tokens for the latent array and m tokens for the byte array. And then c and d are just the length of the feature dimension. Now, the key in cross-attention and reducing the complexity is we want to choose an n that's a lot smaller than m. So for example, when we're using an image, we're using the actual pixel values as tokens. So m will be something like 50,000. But our latent array, this number of tokens, is going to be 512. So we have a lot smaller n, and I'll show how this reduces the computation. So to kind of visualize our cross-attention, we have our latent array and our byte array here. Both of them will go through a layer normalization before calculating the queries, keys, and values. Now, the shapes of these queries, keys, and values for the query, we're going to have n cross h, so those n tokens, and then h is a hidden dimension. And then keys and values are m cross h, so m is the tokens for the byte array, and h is that hidden dimension as well. And the hidden dimension is just so that we can actually perform the self-attention properly. So using the queries and keys, we get our cross-attention map of size n cross m. We'll run that through softmax and then bring in our values. We'll pass those through a linear layer and then add on the initial latent array to get our output of size n cross d. And to focus a little more, the key for this cross-attention is going to be this cross-attention matrix of size n cross m. So if we were performing a self-attention on the image pixels, this m is going to be about 50,000. And so we would have an m by m matrix here instead. And so the number of values in this would be 50,000 times 50,000. And that's a little too much for computation. So by using this latent array and using n tokens of 512, we'll get a 512 by 50,000 cross-attention matrix, and that reduces the complexity by a lot. And so
Brendan, do you know what's the h value here? What's number h?
It's not mentioned in the paper what the h value is. So I couldn't find anything on that or in the code about what the h value is.
Okay. I mean, it must be in the code because otherwise how the code would run, but maybe it's not obvious, right? Okay. Okay, thank you.
So a quick complexity analysis of our model. This is the basic attention calculation. And in here, the query times key transpose is our bottleneck because this is where we create our attention maps. Now there's two types of attention in the perceiver. There's the cross attention and the self attention. I'll go through cross attention first. So the runtime of cross attention is going to be big O of n times m. And this is because our queries are taken from that latent array, which has n tokens, but our keys are from the byte array, which has m tokens. So that's where we get the n times m. Cross attention is done once per cross attention module. And so for self attention, we actually have a big O of n squared because both the query and the key are coming from the latent array. We're not using the byte array in our self attention. So we get an n squared runtime here. And this is done L times per transformer, where L is just the number of transformer layers. So overall, the complexity is going to be big O of n times m plus ln squared. And this is going to be a lot smaller than if we were to just perform self-attention on the byte array, because we'd get a big O of m squared here. So to construct the byte array, we have to take a little bit of a different approach for each modality. So for images, they'll use the individual pixels to create the byte array. So for a 224 by 224 image, there's about 50,000 tokens. For videos, they'll use a tubelet of 2 frames with 8 by 8 patches. That ends up giving us around 12,500 tokens for a 32 frame clip. And then for audio, there's actually 2 different ways they extract the byte array. They'll use the raw patches, which gives a token size of 480 for 1 clip. And then they'll use something called MEL spectrogram. We won't go too deep on this. It's just a different way of extracting audio features. But this gives us a token size of 4,800. And then for the point cloud data, this is just dependent on the number of points that you have in the cloud. Now, for position embeddings, the authors experiment with two different kinds. They'll do a learned embedding, and they'll do a Fourier feature embedding for the position. So I'll talk about this Fourier feature embedding. The goal of it is to increase the dimensionality of our input channel, so the number of features we have per token. And it also provides positional information. Now, because our perceiver can take any type of input, as long as you can deconstruct it into a byte array, this positional information gives us a little bit of an inductive bias, depending on what we're using. When we get the full position embedding, they just concatenate the embedding onto the input tokens. And so here's our equation for the position embedding, the Fourier feature position embedding. They'll do this sine and cosine alternating with a frequency f, which ends up just being 2 to whatever power. This xd inside each sine and cosine is the position value along whatever dimension you're calculating. And k is the number of frequencies that we have. And you'll notice that after we calculate all these sines and cosines, they do concatenate the actual value of the position at the end. So as a quick example, if we're doing the position embeddings for an image, and we're doing it for the pixel at position 1, 0.5, the number of frequencies is 64. They'll calculate one embedding for the first pixel value, this x value 1, and then they'll do another one for the y value 0.5. And then they'll just concatenate those two together to get the final position encoding. So overall, the size of the encoding is going to be d, which is the number of dimensions, which in the case of an image is 2, times this 2k, which is because we do a sine and cosine for every single frequency k, and then plus 1 because we add the raw position value at the end. I'll go over a few architecture details before we get into some experiments and how they train the perceiver. So the latent transformers are just a basic transformer structure. They do self-attention with multi-layer perceptrons and whatnot. And as I just mentioned, the cross-attention and self-attentions are always followed by a multi-layer perceptron. And typically in the architecture, they're going to alternate the cross-attention module and the latent transformer. However, they do an ablation study where they put all of the cross-attention modules at the beginning and then do all the latent transformer models. Now, there's a few different architecture variations based on what modality we're using. So when they're training for images, they use 8 cross-attention modules, and again, alternating the cross-attention and latent transformer. And then all the latent transformers have 6 layers to them, so 6 self-attentions per transformer. And then the byte array size is this 50,000, like I mentioned earlier. When they're performing video and audio learning, they shorten the depth of the architecture quite a bit, so they only do 2 cross-attentions, but they increase the number of layers in the transformer up to 8. And then our input byte array is going to be 12,500 for the videos, and then either 480 or 4800 depending on which audio we're using, the MEL spectrogram or the raw audio. And then when they use the point cloud, they stick with only 2 cross-attention modules, but they bring the latent transformer layers back down to 6. And again, the byte array size is just based on the number of points we have in the point cloud. Now, there's one more thing that the authors change about the normal training method, and they use this LAM optimizer. So if we were to look at a normal optimizer calculation, they'll do the new weights for a time step are the old weights plus the learning rate times whatever update we're doing. But for the LAM optimizer, there's 2 changes that they make. The first change is that they normalize the update at every layer of the model. And the second change is that they scale the learning rate at every layer of the model as well. So if we have a gradient for layer I at time step t, and some scaling factor function based on the normalized weights at that layer, our new update equation is this new time step is the old weights minus, and then these first two is just scaling the learning rate for that specific layer. And then the last part of the equation is the normalized gradient for that layer. Now this isn't something that the authors introduced. This is from a previous paper, and it was shown to decrease the time you need to train on BERT, and that's why the authors use it here for the perceiver. So now I'm gonna pass it off to Josh to explain how we do classification and some of the experiments.
All right. Can you all see my screen?
Yes.
Okay, perfect. All right, so for classifications, the final output from the perceiver transformer is a vector of size n by d, which is averaged over n to create a 1 by d array of logits. This array of logits is then passed through a linear classification layer to get the final classification output for the modalities. For the data sets, the authors use ImageNet for image classification, AudioSet for audio and video classification, and ModelNet 40 for point cloud classification. When experimenting with ImageNet, the authors use inception-style pre-processing with image size of 224 by 224, RAND augment at runtime to augment the images, and the LAM optimizer instead of SGD, as Brandon mentioned before. The authors then train for 120 epochs with a learning rate of 0.004 decayed by a factor of 10 at epochs 84, 102, and 114. For ImageNet training, the authors also use, or make note that they use the XY coordinates of the cropped image when generating positional encodings. The reason for this is they found that using the pre-crop coordinates allow a perceiver to memorize the pixels associated with unique features in the image, leading to overfitting. Perceiver would effectively latch onto a small number of pixels if they have the same features or RGB positional features. The cropped coordinates augment the position and aspect ratio in such a way that it breaks the correlation of RGB values with the positional features. For the ImageNet training, they had 8 cross attentions that flipped between the cross attention and the transformer. The transformer was built of 6 blocks of the self-attention layer and 1 head per block. Weights were shared for the second cross attention onward. They were not shared from the first cross attention through to the 8th one. And the reason why is that they found that sharing weights with all cross attention led to instability in the model. This final model resulted in about 45 million parameters. For comparing on ImageNet, they used ResNet 50 and VIT for comparison. They also passed the Fourier features to ResNet and VIT as well for a more fair comparison. And they also used a transformer that receives a similar pixel input that perceiver does, though it's important to note that this transformer does not have the latent array that perceiver has, and therefore has a much higher complexity when doing its self-attention, resulting in a much smaller input size of 64 by 64. And we can see here that perceiver does outperform even when ResNet and VIT are given those Fourier features. The authors then went on to experiment with ImageNet permutations. And these permutations were done by taking the RGB values at specific pixel indices and permuting those indices across the image in a deterministic pattern. An example of what this would look like on ImageNet, we see here is an image of a 9 with a bunch of different permutations of that image. Now, the position features are generated before the permutations are made, which allows the model to infer the spatial positions without being able to use modality-specific information, specifically locality, to learn the classification. It instead forces the models to utilize those feature informations to learn the classifications instead. And we see that perceiver is capable of learning the images with minimal prior knowledge in the case of those Fourier features, because they do provide some positional information, and with no prior knowledge about positional embeddings in the case of those learned positions. The authors do note that when they use learned positions, they only have 1 cross-attention layer as opposed to all 8 because using all 8 resulted in instability in the model. Now, although this experiment does seem a bit contrived, because very often, you're very unlikely to come across images that look this way, that are so permuted that we as humans can't even recognize them. The point is to show that perceiver is capable of learning these images without any form of inductive biases, without any form of modality specific or domain specific information. All right, the authors also show the output from different cross-attention layers. We see here the original image of a dog and the output after cross-attention layer 1. It's important to note that this is not overlaid on the original image. This is the raw output from that cross-attention layer. And we see the outputs from cross-attention layers 2 and 8. And as you can see, there is a bit of a lattice pattern forming with the cross-attentions. Even at 1, you can see a bit of a lattice pattern forming here. And especially in cross-attentions 2 to 8, it's almost like a tartan pattern. And if you're wondering what that looks like, it looks like that. This seems to indicate that the model is learning those Fourier embeddings when going through all the cross-attention layers. And there are slight variations between attentions 2 through 8, which indicates that each of these subsequent layers are paying attention to different groups of pixels, which is important to note because layers 2 through 8 share weights. So as they go through the layers, they're getting more and more refined. Here we see a much larger list of the outputs from the cross-attention layers. This block here at the top comes from the first cross-attention layer, the second, and then the 8th. And as you can see, you can very clearly see the dog in the first cross-attention layer with a bit of a lattice forming and a much harsher lattice in the 2nd through 8th cross-attention outputs. Now, it's important to note that these lattices were not present in the cross-attention for the learned position encodings. In fact, the learned position encodings were quite similar to the first cross-attention layer without any form of a lattice. So it still has that blur. You can still see the dog in most of these images. It's a little harder in some, but there is no lattice pattern forming in these attention outputs. Right, so I will now pass it off to Alejandro, who will go over audio set and point cloud experiments.
Can everyone hear me?
Yes.
All right, cool. So for the audio set training, there is 2 iterations of the attention that is done. Here it's different from the ImageNet. Before it was, I believe, 8. So here they reduced it to 2. And then for the self-attention blocks in the transformer, they increased it to 8 instead of 6. That was used on the ImageNet. The weights are not shared during the audio set because there's only 2 of those attention iterations, and it was trained for 100 epochs. For the audio input, the input is either generally a raw audio file converted to a byte array or a spectrogram converted to a byte array. For video, it is going to be that 2 by 8 by 8 tublet plus the 3-dimensional Fourier features. This produces a space-time patch. And for both, there's an input that can be combined with both audio and video input. And that's concatenating the video space-time patches with the raw audio vector. Or doing that with the spectrogram values. So either raw audio vectors or the spectrogram. Performance-wise, it was on the audio set benchmark, which is over 2.1 million handset video and about 6,000 or 5.8 thousand hours of audio. Here, it doesn't seem to be the best in really any category except for the raw audio and the perceiver, but it does score pretty competitively. Specifically, the CNN14 is specifically built to be trained on audio, and so that's one of the major reasons why it scores higher. Same thing for the intention AV fusion. It's specifically made for audio and video in this case. So here I'm going to show a attention maps that are trained on about 61,440 raw audio samples. And so in these spectrograms, the width of the input would be the time domain, and then the height would be the audio frequency. And so, one thing we can see is that, it seems to be influenced by the audio frequency in the first cross attention, but that seems to be later replaced by some of the learned Fourier features in the second cross attention. And here's another sample of that same visual. For attention maps on video, this is now trained on 2x4x4 video patches samples. And then here we see that there's the network is pretty sensitive to video input, as you can see that there's still residual as partial temporal structure in the first and second cross attent, and that seems to be evident as well in the second sample. Here the forgot to mention this, but the columns are going to be frames. So across the width of this image here would be the frames of the video. Now this is the attention maps trained on both video and audio. The paper kind of mentions there's not really much to be deduced from this information. It's kind of hard to really see anything visually from the attention maps. Maybe perhaps that could be like influenced by the video. And then for the video input that's trained on both video and audio, here we still see a very strong influence of the video structure in both the separate cross attents. For the point cloud input, that is represented by an unordered vector of points in space. These points are zero-centered, and then augmentations such as point scaling is implemented. These unordered point cloud vectors then fly into a byte array to be inputted. And then here, in this benchmark, the ModelNet 40, it didn't quite compare to the state-of-the-art model because PointN is specifically trained for point cloud data, and as these inductive biases pertain to that data, but Perceiver does score higher than other implementations, and it's still competitive in that respect. For the ablation study, we are showing here at start is all the cross intent layers at the beginning of the architecture versus interleave where they're kind of placed in between the latent layers. And so as you scale higher, you can see that the interleave produces a higher accuracy rather than placing them on the start. So, and in a different evolution study, they checked if basically seeing if they just put a bunch of cross-attend layers in the beginning of the architecture and scaling that, and they do see increase in performance doing that experiment. But they do run out of memory if they increase too much layers. And in a separate another study, they just pointing out that weight sharing basically helps them not overfit the model, and so it is done in between the 2 to 8 cross tension modules in the architecture, and the weight is shared across all latent transforms in the architecture. And then here we can see that the latent index dimension that if it's scaled, improves accuracy as well. And so that increasing the dimension will scale up with the accuracy. For the latent channel dimension, that's not so much the case. It does scale up to a certain degree until you hit 512 channel dimensions, and then you start overfitting. And then for the amount of self-attention and cross-attention layers, it does seem that if you were to scale those, it also scales with the improves the accuracy. And so, well, until it plateaus. So that. For conclusion, the perceiver model prioritizes the flexibility of an input over specifically trained modalities. So this is shown, with the different type of modules you can use, audio, the images, the video, and so the different modalities can be combined. So you can combine audio with video. So it's pretty novel, and then the minimal usage of inductive biases do affect performance in different benchmarks. So in the example of the point net's specifically designed for point cloud performance, and perceiver is not. So that does affect the performance. But ultimately, it does provide competitive results across different modalities and resources.